Now in this short video, we'll go through the concept behind the Nernst equation. This Nernst equation gives us the idea as to how to calculate the equilibrium potential, or what we also name as Nernst potential. So let's have a look. Now here in this slide, we see that the equilibrium potential for a particular ion across a membrane can be calculated. It means that we do not require as such all the experimental procedure to find out how much is the equilibrium potential for that particular ion. If we provided that if we know the concentration of that particular ion at the ECF and the ICF. So here the equilibrium potential can be calculated by this formula here. E stands for equilibrium potential, and for that particular ion there is a non-formula of the 61 by valency. Z stands for the valency of that ion, and then logarithm of the concentration of that ion at the ECF by the concentration of that ion inside, okay, that is in the ICF. So CI stands for inside and O for outside. O is ECF and I is ICF. So let's have a look at this, how exactly to calculate for this potassium and sodium the equilibrium potential. So the E ion, as I said, stands for equilibrium potential for an ion, that is given in millivolt. 61 is basically a constant that incorporates the universal gas constant, absolute temperature, and an electrical constant known as Faraday, along with the conversion of the natural logarithm ln to the logarithm to base log. Okay, so we see that Z stands for the ion's valency. So since if we have to calculate for potassium or sodium, then the valency of both the ions would be 1. And concentration outside is that concentration of the ion outside the cell in millimole per liter, and then concentration inside the cell in the millimole per liter. Now say for example, if we know that the potassium, to calculate the equilibrium potential for the potassium, if you know that 61 by valency 1, so it makes 61 log. The concentration outside of the potassium in millimole, say for example, the value is 5 millimole, and inside we know that that is in the interstellar fluid. Potassium is in higher concentration, that's 150 millimole. So 61 log 5 by 150 millimole give rise to be log 1 by 30. So log 1 by 30 has a particular value of minus 1.477. So 61 multiplied by minus value of log 1 by 30 give rise to the minus 1.477 into 61. That brings about to be minus 90 millivolts. So that is how you calculate the equilibrium potential for the potassium. Now the equilibrium potential for the sodium, how to calculate it? The equilibrium potential for sodium can be calculated with the same very formula, that is 61 by 1, that's the Z stands for the valency for the sodium, so see that makes it 61 log, and concentration outside of the sodium, that is in the ECF, is 150, just opposite to that of the potassium, and then inside of the compartment, the interstellar compartment, would be 15 millimole of the sodium, that is in lesser quantity than the outside. So that makes 61 log 10. So 150 divided by 15 makes 10, and then log 10 is, the value of the log 10 is 1. So the equivalent for the potential for the sodium would be 61 multiplied by 1, that is 61 millivolt. So that's how we calculate the equilibrium potential for the ions. How much voltage that they would create, and at what voltage they would stop moving despite the favorable concentration gradient between two compartment. However, if you look at in the cell, there is not only one movement, one ion moving across the cell membrane, that is only the sodium or the potassium, but rather it's a dynamic process, and these ions are always in a state of the flux. They are moving down from one higher concentration to the lower concentration, given the cell membrane is permeable, and we know that the cell membrane is more permeable to the potassium at rest, and then than the sodium. So let's have a look at this. Then how exactly the at rest, if those excitable tissues can give rise to the potential, membrane potential, then how exactly would be the value given rise by this movement of the ions across the cell membrane. So equilibrium potential cannot be the resting membrane potential. because of this dynamic state of the different ions moving through this plasma membrane or cell membrane. Now, the cell membrane is always more permeable to the potassium at rest, and potassium would move from its higher concentration, that is in the ICF, to the ECF, and sodium is always in higher concentration in the ECF, and then the sodium moves from ECF to the ICF. So the potassium, which is the cations, will move, causing more of the positive ions outside in the ECF, whereas the sodium, which is higher in concentration but less permeable than the potassium, would try to neutralize the negative ions inside the cell, as the sodium is also the cation, so it tries to neutralize those negative ions here. So as shown here in this diagram. Okay. However, the potassium is cation, sodium is cation. This potassium cannot neutralize the sodium outside, but the sodium can, because the ICF has more of these negative ions inside because of the phosphate and the proteins. Now we see that the chloride is in excess in the ECF, okay, than in the ICF. Okay. So however, this chloride are freely permeable to the cell membrane, and then they are equally distributed most of the time on both the side of the plasma membrane. So that ion does not make much of the difference for the creation of the membrane potential of the cell which is at rest, and hence resting membrane potential primarily accounts for those movement of the two ions, that's potassium and sodium. But since the membrane is more permeable to the potassium accounts much for the creation of the resting membrane potential in a excitable cell. So what exactly gives rise to the resting membrane potential? Because the membrane at rest is 25 to 30 times more permeable to potassium than to sodium, potassium is the one that decides the resting membrane potential to a much greater extent than any other ion does. Okay, and potassium alone, however, can have the equivalent potential of minus 90 millivolt, and we know that resting membrane potential of most of these neurons are minus 70 millivolt. Okay, so what creates that lesser negativity than the equivalent potential for the potassium, despite the potassium is freely permeable as shown here in this diagram, potassium moving out in excess? Okay, that is because the sodium counterbalances the charges of the negative charges inside the ICF. Okay, when the potassium moves out, the sodium, which is also slightly permeable for the plasma membrane at the rest, enters into the ICF as the concentration gradient favors from the ECF to the ICF for the movement of the sodium. So that basically causes slightly neutralization of those negative charges, and hence minus 90, the millivolt of the minus 90, which would have been established by the potassium alone, has been slightly brought down towards the lesser negative, towards the minus 70 millivolt by this movement of the sodium ions from the ECF to the ICF. So sodium entry neutralizes, or say cancels, some of the potential that would have been produced by potassium alone if sodium were not present, and hence basically the resting membrane potential in a nerve fiber is minus 70 millivolt and not that of the equivalent potential of the potassium, which would be minus 90 millivolt. Thank you for listening to this video. I hope that the concept for the creation of the resting membrane potential and then the Nernst potential could be understood through this short video.